Welcome to waiting lines. Something that some of us really do not like to do is wait in line. It's also known as queuing theory. You actually may have done some of this in your stats class using Poisson distribution. So we're going to talk about the arrivals, the waiting lines, and the service times. We're going to mainly talk about single channel. We're going to do a cost analysis of the waiting line. We're going to talk about multi-channel. We're going to apply constant service times and limited population models. So studying waiting lines, very important. And they're not just waiting lines for people. I'm sure you can appreciate that having stood in line many hours in your life, that comes to mind. But it's also waiting lines when a product is waiting to go into a machine. The same mathematical models are used for an item that is about to be fed into a machine. So they're very common in manufacturing and in service areas. And companies study this very closely to see how long people are waiting and how long the line is. Many years ago when I worked for London Drugs, they had this as a standard. One person at the front having, when they're going to leave, getting their items scanned. A maximum of 2 people waiting. And so you have a person being serviced and then you have the waiting time. The two of them combined are called the service time or the system time. And so if there was one person having their item scanned and 2 people standing in line, fine. But as soon as there was the third person standing in line at the till, even the store manager would go and run the tills. So you have the arrivals. You need to know the population size, behavior, etc. Normally we use the Poisson distribution. We have limited or unlimited length. We'll talk about finite and infinite. And then again, the service design. So you can see this, you can observe this next time you go to the mall and you see a waiting line at a kiosk for food. So here's an example. No, even though this is David's car wash system or Dave's car wash system, no, I didn't label this. So you have the cars arriving, which is infinite, by the way. So they arrive, then there's the waiting time. In this case, that's the one under the squiggly bracket, the 3 from the van to the car at the front. Then there's a car in the car wash itself, and then they exit the system. So in this particular case, the waiting time, as you're waiting to get serviced, then the service time while you're actually in the car wash. And I don't know about you, but when I've actually taken my car through car washes, I actually pay attention to stuff like this. Because people, when they're waiting, that's the part that people find frustrating. But there's ways you can design the actual car wash so that a car can be being dried and a car can come in the other end and start to get that pre-wash. I'm sure most, if not a lot of you, have gone through car washes, so you understand what I'm talking about. And then there's others where they have to completely be dried before the car, it will open. And that slows everything down. You can produce a lot less cars and people get frustrated with that. But it is an infinite queue because there'll always be more dirty cars. So infinite and going to post-secondary, there's an infinite queue. There's students who are currently 12 years old who will come to the post-secondary school that you're at. There's children who are 2 years old. There are children that are not even born yet. Some of them might even be your children one day. So there is an infinite number. We will never run out of students wanting to come to post-secondary. Or it's finite. Obviously, there's a set limit on it. So there's a finite amount at one time. As I mentioned a couple times already, it tends to follow the Poisson distribution. Some of the the characteristics we're going to have them not switch lines or back it or leaving the line. All right. You tend to have first in, first out is most common. Single channel is if you walked into a bank and there's one ATM machine. Multi-channel is there's more than one bank machine. Single phase is that bank machine does everything. You can deposit money, you can withdraw money, you can pay bills, a whole bunch of things. If you have to go and go through multiple phases, then and see multiple people. So let's say you talk to a person and then you go to another person, and sometimes you need to do that depending on the service that's provided, and that would be multi-phase. We're going to focus on single phase. So in this particular case, here's an example of single channel multi-phase. You get your product, like you order it, you pay for it, and then you go to the next window and you get the item. If you paid for it and got your items all at the same window, that would be single channel, single phase. Now, a lot of places like a McDonald's now, or some of the fast food places, at Tim Hortons, they have dual lines, and that's much more advanced. And this is done for them by Tim Hortons or McDonald's. The average owner of a Tim Hortons or McDonald's has no clue how to calculate this. They understand waiting lines, but they have no idea how to do the actual math. And there's certain standards set for how long people will be in line. And you've seen advertisements sometimes, or it's been a few years, but McDonald's used to have, if you don't get your product within a certain length of time, the next time you get a discount. Because McDonald's prides themselves in speedy service. And here's just some other examples. All right. So the average time the customer spends in the queue, the average length of the queue, the average time the customer spends in the system, which is the waiting time and the service time, number of customers, probability the service will be idle, what percentage of the time the system is busy. So that will be the reciprocal of the idle time. So if the idle time is 20%, the utilization is 80. And then we're going to talk about, and you would have done this in statistics class, probability of specific number of customers in the system. And then again, here's the optimal point where you have too many people providing service or not enough. Because sometimes people will walk away. And just as a side comment, this gets studied, and people are becoming less and less patient. For example, at Christmas, a couple of years ago, say 5 years ago, people were actually willing to stand in line when there was 10 people. Once there was more than 10 people, a lot of people just drop their product and walk out the door. Too long a lineup. In the last 5 years, that number has dropped to 8. So this is an example of where you can't just do what you did before. Now you're going to have 2 customers, customer 9 and 10, leave, and they're going to go buy their product somewhere else. So people are less patient than they were before. So again, here's just some information. We've already kind of gone over all this. FIFO, first in, first out, Poisson probability, etc. Single channel. And I'll go through several examples in the book, and that will hopefully help you understand it even better. Thank you for listening.